Hello everyone, welcome to the course Unsaturated Soil Mechanics. Now in this first lecture I will take your attention to the scope of this particular course and possible applications in the field of geotechnical engineering. Let us look at some reference textbooks available on this topic. The first one is Liu and Lycos. These are the two authors, Ning Liu and William Lycos. They have developed a book on this particular topic called Unsaturated Soil Mechanics in 2004, which is a very popular book. And earlier book was Soil Mechanics for Unsaturated Soils by Fredland and Rahazo in 1993. And this is probably the first book available on this particular topic. And Fredland's contribution in unsaturated soil mechanics is significant, and often Fredland is considered to be the father of unsaturated soil mechanics for his contribution in this particular topic. During his tenure as professor at University of Saskatchewan, Canada, he has developed many concepts on unsaturated soils, and especially the concepts taken from soil physics and soil science are brought into engineering, and he has developed many concepts, and those are all compiled into one textbook, that is Soil Mechanics for Unsaturated Soils in 1993. And most of the concepts that are given in Liu and Lycos are extended from the earlier topics that were earlier concepts developed by Fredland and Rahazo. And for this particular course, most of the concepts are taken from these first two books. And you have another book by Lalui on mechanics of unsaturated geomaterials in 2010, which contains most advanced topics of unsaturated soils. Some concepts like osmotic suction, matrix suction, and osmotic component of matrix suction, such concepts are considered from this textbook for this course. And the other book is Soil Physics by Marshall, Holmes and Rose. This is a wonderful book on soil physics. Many physical chemistry concepts of soils are taken from this textbook and then considered in this course. And the next book is Soil Physics with Hydrus, contains many concepts on modeling the flow behavior in unsaturated soils and the application of Hydrus software, which is a freebie, and those are discussed in this particular textbook, and some modeling aspects of unsaturated flow behavior are taken from this book. And the last book is on physical chemistry by Atkins and Paula. This is an excellent book on physical chemistry. Many fundamental concepts like Kelvin's equations, the cavitation, condensation, vapor pressure lowering, Raoult's law, and many other concepts are taken from this textbook and explained in this course. Let us begin in understanding the shortcomings of our soil mechanics for understanding the soil behavior. It all starts with Coulomb, who proposed the friction laws, which can be described by the simple mechanism where a simple block which is sliding on a ramp, which has a weight component, and there is a frictional weight component, and there is a resistance that is offered, that is a frictional component, and there is a normal component which is acting on this block. This is a free body diagram of the block. According to the friction law, the frictional force is proportional to the normal force, and this is the material constant, which is independent of the normal force or weight of the block. Either a block sliding on a ramp or a block is moving against a surface, or two individual grains shearing along this plane, or a lump of particles which are sheared along this shear plane when there is a normal load. All this would represent a failure along this shear plane, and Coulomb's principle is applicable. So this is the motivation for developing the shear box test apparatus, where you have a soil sample which is sheared along this predefined shear plane by applying some normal load, and the same equation is valid. In terms of stresses, we represent this using tau f equal to mu sigma. Sigma is normal stress and tau f is shear stress at failure. These are the shear box test results. For the same normal stress, a given soil behaves in this manner, either in this manner or in this manner. Soil shear stress gradually increases with increase in the shear strain and reaches a critical value, or the shear stress approaches a peak value and decreases and approaches the critical value. Generally, the dense soils are over consolidated clays where OCR is more than 2, they exhibit this behavior, or loose sands or normally consolidated clays exhibit this behavior. When you conduct tests with different sigma by changing the normal stress, you will get the relationship between tau F versus sigma. So therefore, using the Coulomb's principle, you will get a material constant called angle of internal friction, that is tan phi here, either mu or it could be represented with tan phi. This is angle phi, this is angle of internal friction at critical state. If you take peak data, the shear stress at peak values, and plot, you may get phi peak, the angle of internal friction using peak values. As this value can change with initial condition, this does not represent the material constant, but phi critical would represent the material constant, because for whatever the densities you use, whatever be the initial condition, this is constant. So therefore, phi critical represents a material constant which is often used in the design. So all this knowledge is from Coulomb's friction law. However, here we utilize you have a two-phase system. You have a soil solids and air in the pore space. Then comes this effective stress principle, where in case if you have a pore fluid in the pore space of the system, when you apply normal force and frictional force, there is a counter thrust that is acting from the pore fluid. So therefore, this is the force that is acting at equilibrium, and this is the force acting at the equilibrium. This is given by Terzaghi, who has given this effective stress principle, and then we modify the Coulomb's law by changing the normal force to effective value n minus u. We add this counter thrust. So essentially, you get a tau f, that is shear stress at failure, is equals to sigma dash and effective stress times tan phi dash. So because of this, soil exhibits different strength during. So soil exhibits different strength depending on the drainage condition, whether you allow the drainage to take place during the shearing or drainage is not allowed during the shearing, would influence the shear strength property of the soil. So we get different strengths, therefore, and in triaxial tests we are able to control the drainage, and we conduct consolidated undrained and consolidated drain tests, wherein we get strength parameters in drain condition and undrained condition. So far we have utilized the soils in considering soils to be a two-phase system, where either you have soil solids and water or soil solids and air. So according to Terzaghi, in his infamous theoretical soil mechanics textbook, he says that the soil mechanics is defined as the application of the laws of mechanics and hydraulics to engineering problems dealing with sediments and other unconsolidated accumulations of solid particles produced by the mechanical and chemical disintegration of rocks, regardless of whether or not they contain an admixture of organic constituents. So in this description, he is defining what is soil, and here he is defining what is soil mechanics. Essentially, the application of mechanics and hydraulics for understanding the soil mechanics. That is what is soil mechanics. But however, in nature, you have unsaturated soil. The geological media between ground surface and regional groundwater table, you have a thick or depth varying geological media which is partly saturated. Essentially you will have three-phase system. So you have pore airspace, pore water, and soil solids. So this is volume of air, volume of water, and volume of solids. So this is volume of voids. Within the void space you have two phases. One is air, one is generally water, or sometimes you may have oil or any other thing. So this is most natural case. So if this is the case, then soil, within the soil at the air water interface, you may have surface tension developed at the interface. This provides additional strength to the soil, and this can change with change in the water content, change in the air content in the system. So for example, we make sand castles at beach side, on the shore. We make sand castles on the shore. Here with sand you can achieve steep angles, an angle which is much steeper than the angle of internal friction. This is because of additional strength that is provided from the surface tension or the negative pore water pressure which is present in the pore space due to the presence of two-phase system, due to presence of air and water. If you go to the sand castles where you find that the angles are steep enough to make it to be molded into different shapes, and these angles are much steeper than the angle of internal friction. If you dump sand from a truck, it assumes an angle which is equal to the angle of repose. Steeper than this you cannot make unless until there is an additional strength that is coming from the surface tension or negative pore water pressure. So in the sand castles we are able to make structures with angles steeper than the angle of internal friction of the soil because of the surface tension effects. So because you have two phases in the pore space, you are able to get additional strength. Therefore in natural slopes they may be steeper than the natural slopes natural slopes are much steeper, and you may see vertical cuts in many a times that would withstood. Therefore in natural slopes, if you see, often you see a vertical cut which can withstand the slope for a very long time without failure. This is all because it has additional strength due to negative pore water pressure in the system. That is because you have two phases in the pore space. So this is all fine. So this we analyze using conventional stability analysis, where each slice is analyzed for force and moment equilibrium, and then we find out the factor of safety. However, when during the rainfall water may seep into the ground surface or the slope, and then the air water interface may disappear because the pore space will be replaced, pore airspace will be replaced with water, and you may have only essentially two-phase system, that is water and soil solids. In that particular case the strength may drop, and which causes a decrease in the shear strength and which causes a landslide. And we have seen several disasters recently in the recent past, like Baduda disaster in Uganda. This is due to rainfall induced slope failure, and this is another landslide in Sikkim and Mizoram, where during the monsoon season you often see these landslides. This is because soil has sufficient strength when it is partly saturated or due to the negative pore water pressure, but this additional strength disappears as water imbibes into the soil system. This is another disaster we had seen recently in India. So essentially in these cases we need to answer these two questions. What is the water flow rate through unsaturated slope? In our traditional soil mechanics, we only learn the flow behavior through saturated soil system using Darcy's law. Whether Darcy's law is valid or not here is one question, because you have airspace through which water will not pass through, but it may saturate eventually with time. So what exactly the flow behavior through unsaturated soils is one question. Another question, The shear strength definitely changes with change in the moisture content, but how does it change? These two questions we need to address if we are analyzing the slope behavior due to rainfall infiltration. This is another situation wherein the unsaturated soil mechanics is very useful. This is a Brahmaputra bank in Bangladesh. Here the banks got eroded, and here you could see the vertical cut in the bank. This is all because the soil is not fully saturated, it's partly saturated, therefore it is able to maintain nearly vertical cut. Here the slope stability plays an important role in controlling the erosion of the stream bank. So the unsaturated soil mechanics principles are again very important and applicable for addressing such problems. And most frequently we encounter such issues wherein the soil mass beneath the foundation either swells, which we call heave, or collapses depending on the type of soil during saturation. So initially in dry state, the foundation soil will have sufficient strength to carry the structure, but when rainfall occurs, the water seeps into the ground, which causes decrease in the shear strength, and either building fails in shear, or if you have an expansive soil, the soil may expand, or if you have a collapsible soil will collapse due to wetting. This causes collapse of the entire structure. The whole structure may sink into the ground, or the entire structure will be uplifted, or there may be cracks that may be appearing, or this whole thing will fail in shear. All these problems are due to the change in the moisture content of the foundation soil due to seasonal effects, which causes change in the shear strength and volume change. So in addressing such issues, we need to address another issue, that is what is the volume change, that is either heave or collapse, that may take place due to moisture content variation under the applied loading, apart from these two questions which we addressed for slope stability. There is an important issue these days is nuclear waste disposal. Even though it is at present India does not require this facility, but then in long term we require such facilities to address the disposal of nuclear waste, high level nuclear waste. According to the Swiss design, the nuclear waste is kept in a canister, copper canister, and which will be dumped or placed at several hundreds to 1,000 meters below the ground surface by making tunneling and reaching the prescribed location, which is much below the ground surface, which is nearly several hundred meters below the ground surface, where the canisters are. These are the canisters which contains the radioactive waste. These canisters are placed, and which is backfilled with bentonite material. Bentonite is a highly expansive clay, high plastic clay, so which is backfilled with. So essentially the bentonite which is available around the canister would contain the radioactive waste element by making the permeability very low. The permeability of the bentonites in unsaturated condition are as low as 10 power minus 16, 10 power minus 18 meter per second. Such a low permeability they create. So essentially, if there is a leakage that happens from the canister, radioactive elements would diffuse through the bentonite. That would take nearly very long time, and which is surrounded by rock mass, saturated rock mass, and you have access tunnels which are again backfilled by the bentonite. Here this is called buffer, and here you have a bentonite backfill. So backfilling and buffering requires the bentonite material to be used, and the properties of these bentonite materials or the characteristics of these bentonites are important, and moreover the mechanical behavior of this bentonite in this particular condition is very important. In this particular situation, when it is when the bentonite is used as a buffer material here and backfilled elsewhere, now there could be a water which may be penetrating from the surrounding saturated rock mass into the buffer material. So in that particular case, the unsaturated flow through bentonite material is important, and secondly, there may be thermal gradients across the bentonite layer. So thermal flow, thermal conduction is important, and the mechanical behavior. When the bentonite is saturated from the saturated rock mass, water which is coming from the saturated rock mass, bentonite applies huge pressure on the surroundings. So this mechanical pressure could be as high as 40 megapascals, it depends on the type of soil. However, so this swelling pressure, this is called swelling pressure, that the bentonite exerts on the surroundings when it is confined and when it is not allowed to swell due to saturation, will be nearly equal to the hydrostatic pressure that is acting at that particular depth from the ground surface. So the mechanical behavior such as this swelling pressure with dry density, and similarly the swelling pressure with water content are important for different soils for understanding the mechanical behavior. So this is a typical data from Butcher and Muller-von Moos here for MX80 bentonite and Montiel bentonite. These are highly plastic clays where the soil is compacted to very high densities, nearly 2 gram per centimeter cube dry density, and it exhibits a swelling pressure of nearly 40 megapascals, 40,000 kilopascals. So the thermo hydro mechanical behavior, because you have a thermal gradient across the bentonite, you have a hydraulic gradient across the bentonite, and the pressure which is generated due to the saturation, because of which the coupled analysis of thermo-hydromechanical behavior of the bentonite barrier is important, and also THM behavior of host rock is important near field, and hydromechanical behavior of shafts and tunnel seals are also required. So THM analysis contains heat transport, water flow, air flow, vapor diffusion, mechanical behavior, thermal equilibrium between different phases. All these need to be coupled and then solved, the expressions, for understanding the bentonite behavior in that particular situation. There is another situation where you have buried pipelines. Buried pipelines are used for carrying the natural gas or any other material from one point to another point. Here the soil which is surrounding the buried pipeline might exert some pressure on the pipes due to change in the moisture content, or they may exhibit a volume change behavior due to change in the moisture content, which causes additional stresses on the pipes, and if the stability of pipes is not sufficient, then it may break and leakage can occur. So to address these issues, we require to understand the unsaturated soil mechanics or unsaturated soil behavior. So another application is cover design in acid mine drainage, in acid mines and in landfills. Cover designing plays a very important role in this particular situation where the rainfall percolation into the system should be controlled. Here the permeability of the cover system should be low enough so that the water generally runs off from the surface and the percolation is minimal. Secondly, if you use directly bentonite type of soils here, it may develop cracks when there is a excess of drying that takes place or evaporation that is taking place during dry periods. So it should have low permeability. At the same time, it should not crack, otherwise in the next season during monsoon, this cracks would prompt the water to enter directly into the system, either acid mine tailings, or it could be landfill liners, landfills. So the permeability of the soils are very important, permeability of the unsaturated soil is important, and the slope stability is also important. This is another aspect which is not addressed in basic soil mechanics. There is osmotic effect. Expansive soils such as bentonites and black-cotton soils, on the clay particle surface they have negative charge surface due to isomorpha substitution. So that attract positive ions onto the surface, and they have there are exchangeable cations on the surface. When there is a moisture that is available, the exchangeable cations get hydrated, and the external surface and internal surface of the clay particles also would get hydrated. And if there is additional water that is available, free water available, then there is a formation of diffuse double layer where the electrostatic potential varies from the clay surface to one particular distance called diffuse double layer thickness. So clay particles exist along with the diffuse double layer, and this is due to the osmotic effect. And when two different particles come close to each other, there is a osmotic potential that is developed at the interplate distance. These osmotic effects are important for controlling the flow behavior, for volume change behavior, and shear strength behavior of fine grained soils or clays. So such osmotic effects are not addressed in basic soil mechanics. The beauty of unsaturated soil mechanics is that the osmotic head and the negative pore water pressure that we call matrix suction head, all these heads are considered in the same head, and we consider for the flow behavior, volume change behavior, and shear strength behavior. So these are the noticeable points. What shear strength parameters we use for the slope stability analysis? Because the shear strength depends on the amount of moisture that is available. If you analyze the soil slope using saturated strength or strength obtained at the saturated state, then it may lead to unrealistic stability analysis, and slope may fail much before the soil approaches the full saturation, if it is going from the drying to full saturation state. And at what rate the water flows through the soil, so that you can couple the flow behavior and the strength or mechanical behavior, so that one can analyze rainfall induced slope instability. And the third aspect is the volume change behavior during infiltration of water under given normal stress, normal load, and development of cracks due to volume changes. These issues can be well addressed using the unsaturated soil mechanics. So therefore unsaturated soil mechanics should be defined as the application of the laws of mechanics, hydraulics, these are anyways used in basic soil mechanics. The additionally interfacial physics, so you can allow the surface tension forces to come in, and then you can explain many things, and physico-chemical mechanisms, so that you can address the fine grained soil behavior, to engineering problems dealing with partly saturated soils. With this I'll stop here, and I'm sure this would provide enough motivation for studying this subject. Now we'll discuss some fundamental principles that are essential for understanding the unsaturated soil mechanics. In this lecture, we'll discuss about the prediction of a phenomenon, how a phenomenon can be predicted. For that, it is important to recognize what are the governing equations need to be invoked, the constitutive relationships. For understanding the constitutive relationship, you need to identify what are the state variables and build the constitutive relationships based on some experimental observations, and determine the material constants, and we predict the phenomenon. We will try to understand today, for any prediction of a phenomenon, for phenomena prediction requires mathematical representation of a given problem. So for example, a simple problem you have wherein an object is falling from a certain height from a tower, and at what rate, how much time it takes to reach the ground is one problem, and or a mass of sphere which is oscillating, which is attached to a spring and which is oscillating, which is having a displacement of y, and prediction of this phenomenon requires a mathematical representation of this problem. When it comes to the geotechnical engineering, we are interested in understanding the consolidation settlements of structure which is resting on soil, and seepage prediction underneath a dam, or it could be a shear failures of slopes, foundations, or any other structures. Let us try to understand. We have governing equations such as conservation of mass, we have conservation of linear momentum, and conservation of angular momentum, second law of thermodynamics, and Maxwell's equations. These are fundamental governing equations we need to invoke for understanding any phenomenon mathematically. Mathematically to represent, and for understanding any phenomenon we need to invoke these governing equations. Now readers are advised to refer, the audience are advised to refer any standard textbook on continuum mechanics for more explanation on these physical laws. These are physical laws. The audience are advised to refer any standard textbook on continuum mechanics for more explanation on these physical laws. So these physical laws need to be invoked for mathematically representing any phenomenon and prediction of phenomena. One of the best textbook could be Malvern, on introduction to the mechanics of a continuous medium. Apart from these physical laws, we also require additional equations to solve the problem uniquely for satisfying the constituents. It is material dependent equations we require. Constituent equations therefore explain the interdependency of different state variables. It is stress, strain, void ratio, effective stress, etc. The proportionality constants of the constitutive relationships are called material constants that represent the fundamental constituents of the system. Material constants may also depend on the state variables. The dependency of material constants on the state variables and one state variable on another state variable through constitutive equations is required for understanding the behavior. Let us identify the governing equations, state variables, and material constants in the basic soil mechanics. Such identification exercise is important for the prediction of physical phenomena or simply the engineering behavior of soils. Let us take the problem of consolidation. Consolidation of clays is a very important subject area in soil mechanics, and also which is very important for prediction of settlements and settlement rates, ultimate settlements and rate of settlement of any structure which is existing on soil. Generally the soil samples from the field are brought to the laboratory and then studied in the laboratory in odometer cells. Odometer cells illustration is given here. So in this slide it is shown the clay sample which is sandwiched between a porous stone, top porous stone and bottom porous stone, and this is fully submerged in water. So the sample is in fully saturated condition, and you apply a normal load P, and generally the cross sectional area, the diameter of the sample would be 6 centimeter and the thickness of the sample is 2 centimeter. So if the load is P applied, then the stress existing on the sample is P by cross sectional area, which is the load by the cross sectional area, which is the total stress that is acting is sigma. So under this particular condition, as there are two boundaries where you have highly permeable porous stones are sitting, which replicates the situation of clay sample which is sandwiched between sand layers in the field. So there is a hydraulic gradient that is developed because the excess pore water pressure at the boundaries are 0, and at the middle of the sample it has a maximum pore water pressure, excess pore water pressure. So there is a gradient that is developed within the sample, and excess pore water pressure dissipates through the boundaries. So in turn the clay sample consolidates with time. So this phenomenon is theoretically studied using Terzaghis one-dimensional consolidation theory. This consists of considering one elemental volume, a representative volume, and the flow through this volume could be considered. Volume of the sample is delta V, and the thickness is delta Z. If you consider the volumetric flow rate Q, which is in the upward direction, and the volumetric flow rate which is coming out, which is Qz plus delta Z. So the change in the volumetric flow rate can be understood. The Qz in terms of unit discharge or flux is small q z times the cross section area. If the length of this elemental cross section area is delta x, then this is delta x times the delta y in the in plane direction, delta y. Similarly, q z plus delta z is small q z. There is a flux plus change in flux with distance into delta z into delta x into delta y. So the change in the discharge volumetric flow rate is nothing but delta q is dou q by dou z times delta x delta y delta z, which is nothing but dou q z by dou z times delta v. So this is the volume of the element. So this quantity is non-zero for transient flows. If it is a steady state flow, this quantity is 0, but because here a transient flow that is taking place, a time variant that is taking place, flow is dependent on time here, that is a transient flow that is taking place. This quantity is equal to the rate of change of volume of voids, because the flux is changing, because the volume of the element is getting compressed. So therefore this is nothing but the volume of voids is nothing but n, that is porosity, which is porosity is equal to volume of voids per total volume. So therefore porosity times total volume is your volume of voids, and rate of change dou by dou t of nv. So therefore, so these two quantities should be equal. This is first equation, this is second equation, and this can be written as, so the dou by dou t of n into delta v can be written in terms of void ratio as dou by dou t of void ratio by 1 plus void ratio times delta v. So delta v is a small elemental volume, and 1 plus c represents total volume. So for small strains one can assume one can approximate this as delta V by 1 plus E times dou by dou T of E. So if when you equate this expression, the second expression and first expression, you get dou Q Z by dou Z times delta V is equal to delta V times delta V by 1 plus E times dou E by dou T. This expression is a mass conservation expression. Conservation of mass is considered here. Here the conservation of mass is considered. So whatever the change in the flux is due to the change in the pore volume with respect to time. So this is conservation of mass, mass conservation principle. So if the conservation of mass is satisfied, then this equation should be satisfied. So here physical law is applied for deriving this expression. Now we can simplify these expressions in terms of known state variables. This left hand side expression of this expression, left hand side of the equation 3 can be written as dou by dou Z of, if Darcy's law is valid, then Qz can be represented as Kz into dH by dz. So because when the load is applied, the gradient is available only on one side in one direction, that is either upward direction or downward direction. So you have gradient that is available only in vertical direction, that is Z direction. So which is equal to Kz times dou square H by dou Z square, if we assume that the hydraulic conductivity does not change with space. That is an assumption. For small strains and consolidation apparatus, this could be assumed. For low plastic soils, etc., and then this assumption should be valid. Assumption is valid. So then representing the head in terms of, this is a hydraulic head, representing in terms of pressure, this becomes a Kz by gamma W into dou square U by dou Z square, because U is equal to H into gamma W. So this is equation number 4. If you consider RHS, right hand side of the equation 3, here we require a constitutive relationship because it is with respect to void ratio 1 plus C into dou E by dou T. Here we require one constitutive relationship need to be invoked. Here we use the constitutive relationship between void ratio and effective stress. So for normal scale, this plots somewhat like this. So the slope of this, if you consider a small change in delta sigma dash and what is a change in delta E. This can be obtained from different loadings. When you load the sample, then change in the void ratio at equilibrium when sigma is equal to sigma dash can be obtained. When excess pore water pressure is nearly 0, then sigma is equal to sigma dash and you get the change in void ratio with respect to sigma dash. This is a one constitutive relationship which is a relationship between one state variable called void ratio and another state variable is effective stress. So we assume that the slope is constant. We assume that this is linear for a small increment of delta sigma. Then the coefficient of compressibility AV is written as delta E over delta sigma dash with negative sign, because increase in the effective stress decreases the void ratio. And if you divide, so now this expression, if you substitute AV here, so you get AV by minus AV by 1 plus E into delta dou sigma dash by dou T. So this is nothing but delta E by 1 plus E, which is strain divided by stress. So this is 1 over bulk modulus called coefficient of volume compressibility times dou sigma dash by dou T. As the left hand side expression is in terms of excess pore water pressure, here also we try to represent in terms of excess pore water pressure. For that we need to invoke the effective stress principle, that is the Terzaghi's effective stress principle says that sigma dash is sigma minus U, effective stress is sigma total stress minus excess pore water pressure or pore water pressure. So here the change in delta sigma is change in delta sigma dash if you take consider, then it is equal to minus delta U, because the consolidation is taking place under the applied normal stress. The total stress is not changing, only the pore water pressure is getting dissipated, and which is replaced, the excess pore water pressure becomes equal to the effective stress. Therefore delta sigma dash is equal to minus delta U. If you substitute in this expression, you get mv times dou U by dou T. So if you equate the expressions 4 and 5, you get the Terzaghi's one dimensional consolidation equation, that is K by mv gamma W into dou square U by dou Z square is equals to dou U by dou T. So this quantity we write it as CV. So CV times dou square U by dou Z square is equal to dou U by dou T. This is Terzaghi's one dimensional consolidation equation. So this is a governing equation which is derived using a physical law, that is mass conservation principle. So this is the mass conservation principle that is used, and we invoked the effective stress principle, and we used Darcy's law here to represent this expression in terms of state variable excess pore water pressure. So the governing equations are generally represented in terms of, the governing equations are generally in terms of state variables. So this, to derive this governing equation, we require additional equations such as the constitutive relationship, that is E versus sigma dash, which is a relationship between two state variables. So here now identify the constitutive relationships, state variables and material constants in this derivation. The equation 3 is a governing equation based on the mass conservation principle. Equation 3 is the physical law, which is mass conservation. Using that we got the governing equation. We utilized E versus sigma dash relationship, which is a constant relationship. The state variables are here void ratio and sigma dash. Even pore water pressure, excess pore water pressure is also a state variable. So these are the state variables. The material constants are AV, coefficient of compressibility, coefficient of volume compressibility, which is nothing but 1 over the bulk modulus, even CV. These are material constants. As we don't measure the excess pore water pressure in the odometer tests, we represent the solution of equation. As we don't measure the excess pore water pressure in the odometer tests, we represent equation 6 to estimate the material constant, one requires to solve this equation 6. As we don't measure the pore water pressure in the odometer tests, we represent the solution of equation 6 in terms of average degree of consolidation and versus time factor TV, and due to unique nature of this relationship and similarity between measured settlement versus time, the settlement versus time relationship, because these two are similar, using this similarity, due to the similarity between U average versus TV and settlement versus time, we utilize either Taylor's method, that is square root of time fitting method, or logarithm of fitting method to estimate the time factors TV 90 and TV 50 respectively, and we estimate the CV from the expression. We use expression TV equals to CV times T by H square, where TV is estimated from the graphical technique. So time is known, at what time you achieve a given TV is known, and drainage path length is known, so one estimates CV indirectly. So essentially we indirectly estimate CV from equation 6 using graphical techniques. So here the phenomena is predicted. So once CV is known, one can estimate the rate of settlement in the field, and one can estimate the total settlement, ultimate settlement, from this expressions. This is possible because we used a physical law, that is mass conservation principle, and we identified the state variables, and we represented a constitutive relationship, that is E versus sigma dash, and we utilized that, and we estimated the material constant, which only depends on the constituents or the material property. So therefore we can predict any given phenomena. We see another example where similarly for steady state flows, the equation 1, that is dou q z by dou z, equation 1, this expression should be equal to 0 for steady state flows. If it is for two dimensional flows, this is nothing but kx dou square h by dou x square plus kz dou square h by dou z square is equals to 0. For isotropic case, the kx and kz is same. This is simply dou square h by dou x square plus dou square h by dou z square. This we solve by invoking velocity potential and stream function, and knowing that these two functions satisfy the Laplace equation, we graphically solve this for estimating the seepage rates underneath a dam. If you have a dam or sheet pile wall, so this is the water which is behind the sheet pile wall, and what is the flow that is taking place can be estimated in a confined environment very easily. Graphically we can estimate, and this one we have already learnt in basic soil mechanics. So here also we utilized mass conservation principle. So there is a physical law. So the head here is the state variable. All the governing equations are always represented in terms of state variables. Similarly, for estimating the shear strength characteristics of soils, we invoke stress-strain relationship, stress versus strain. Stress versus strain relationship. In direct shear, we get the shear stress versus shear strain relationship, where for normally consolidated clays, they exhibit this behavior. Normally consolidated clays or loose sands exhibit this behavior, and over consolidated clays and dense OC soils or dense sands exhibit a peak behavior, and after that the stress decreases. NC or loose sands. So here we obtain the failure, shear stress at failure for critical state, and from this is a stress strain relationship, and this is a shear stress versus shear stress at failure versus sigma at failure. This whole test is conducted at 1 sigma, and for different sigmas, if you conduct different shear stresses you get, and from that you can obtain either a straight line joining from origin or with some intercept. So these are the material constants, phi critical and cohesion. These are the material constants, and sigma f, tau f are the state variables. Similarly, tau and shear strain, these are state variables. So the constant relationships are tau versus sigma. If it is a drain test, intraxial test, then it could be sigma dash also, and tau versus gamma, or in traxial test you get delta sigma versus strain. So these are the constant relationships. We have. So therefore, for the phenomena prediction, you require first physical observation. For example, in case of consolidation, this is settlement versus time, settlement versus time, and you have governing equations which are derived from the physical laws. Here it is a mass conservation, this is for consolidation problem. Then after getting the observation settlement versus time, you invoke the mass conservation principle and to derive the governing equation, and you identify the state variables. Here the state variables are sigma dash, void ratio, u, etc. You identify the state variables, then construct a constitutive relationship using experimentation. So you build void ratio versus sigma dash. So this is the constitutive relationship which is obtained from the experimental observations, E versus sigma dash. Then identify the material constants such as AV or MV, and finally CV. Then you predict the phenomenon, because once CV is known, CV is obtained, you predict at what rate the settlement is taking place. You get a theoretical settlement versus theoretical settlement versus time. So once you theoretically obtain the settlement versus time, you compare with the measured or observed physical observation, that is settlement versus time. If that does not match, so then you need to refine whether you have considered all the physical laws for building the governing equation or not. You need to check, are there any more state variables need to be recognized and constitutive relationships need to be built, that you need to check. For example, in one case, that is a consolidation settlement of soft soils, which is of concern in many applications like mine tailing applications and other applications, and phosphate clays or tailings deposition. In all these situations, the soft soil sedimentation or soft soil settlement is very important. In such situations, the Terzaghis one-dimensional consolidation theory overestimates the settlement rates. That is because the soft soils would settle even because of its own weight. Here the conservation of momentum, that is force equilibrium, is not invoked here. because we are assuming that sample size is very small, 2 centimeter thick, and we are ignoring the effect of self weight. So when we invoke the self weight, when we invoke the conservation of momentum principle, that is force equilibrium, then we can predict the behavior very well. That is done by Gibson. And also in this particular derivation, one also need to express another constitutive relationship, that is K versus E. The hydraulic conductivity in the sample. So if this is the consolidation sample, you have porous stones at the top and bottom, or sand which is at the top and bottom. Now as soon as the load is applied on the soil sample, you have pore pressure at any given point at time t equal to 0, pore pressure at any given depth is equal to the applied stress. But just after time t equal to 0, the pore pressure at z equal to 0 and z equal to L, it becomes 0, and this is the pore water pressure distribution you get. Pore pressure is, excess pore water pressure is maximum at the center, and they are 0 at the boundaries. So this is the condition. If the excess pore water pressure is 0 at the boundaries, two boundaries, then the sigma dash should be maximum here, and from the expression of sigma dash versus E relationship, when sigma dash is maximum, the void ratio is minimum. So if the void ratio plot is made with depth here, so the void ratio should be smaller here and larger here and smaller here. So this is how the void ratio changes. If the void ratio changes in this manner, the hydraulic conductivity also changes similarly. Hydraulic conductivity should be smaller when the void ratio is small, and should be higher when the void ratio is large. So K also changes accordingly. So therefore this expression is also invoked. This constitutive relationship is also built. This relationship is also obtained from the consolidation tests, and this is also used in the analysis. And finally, the Gibson's model, which considers the Lagrangian coordinate system, where the element also changes. The element initially we considered, this also changes with time. That is also considered by considering the Lagrangian coordinates, and it considers the another physical law, that is conservation of linear conservation of momentum, that is considered. So that means force equilibrium is considered, and the expression for sigma dash versus E and K versus E both are invoked, and Gibson's expression predicts very well the consolidation behavior of soft soils. Thank you.